Now let's talk about heat capacity. Before we get into this section, I will note that we skipped section 9.2 along the way, but we will come back to it after introducing these concepts. I think it helps to talk about heat capacity before we go back to chapter 9.2 and talk about things that involve enthalpy. So heat capacity, we'll represent that with the letter capital C. What we define heat capacity to be is the amount of heat that's absorbed by a substance divided by the increase in temperature that that substance would experience as a result of the heat absorption. Put another way, you can say that C is equal to Q over the change in temperature. And that's how we would find heat capacity. Now, it's helpful to take a look at an example of a value of a heat capacity. So let's look at the heat capacity of liquid water, which is given as 4.18 joules per gram per degree Celsius. Now, it helps to take a look at the units and think about what they're telling you in words. And when you convert the units into words, what this is telling you is that you would have to add 4.18 joules of heat to 1 gram of water in order to increase its temperature by 1 degree Celsius. What a heat capacity is essentially telling you is how much heat do you have to give something in order to change its temperature by 1 degree Celsius? Or another way of thinking about it is a heat capacity tells you a substance's tolerance for heat absorption. Water can absorb, right, has a tolerance for absorbing 4.18 joules of heat before 1 gram of water raises in temperature by 1 degree Celsius. Now, different substances have different tolerances or different capacities for heat absorption. So aluminum, on the other hand, has a heat capacity of 0.9 joules per gram per degree Celsius. And what that means is that aluminum can only tolerate 0.9 joules of heat before 1 gram of it raises in temperature by 1 degree Celsius. Water has a higher heat capacity than aluminum, right? 1 gram of water can absorb more heat than 1 gram of aluminum before the temperature rises by 1 degree. And the reasons for that will be discussed in a little bit more detail in Chem 1C when we talk about things like hydrogen bonding. But it's important to know that different substances have different tolerances or different capacities for heat absorption. Now, starting with this equation, C is equal to Q over delta T, we can see how this equation could be rearranged to allow us to calculate heat flow for a particular process. Because if you multiply both sides by delta T and solve for Q, you find that Q is equal to heat capacity times delta T. So this would be how an equation that you could use to calculate heat for a process. This is kind of like a base equation from which we can come up with different variations. And the variations that we would come up with will be heavily dependent on the units of heat capacity. So if, for example, you see that heat capacity is given to you in units of joules per mole per Kelvin, then you would need to multiply by the number of moles, giving you Q equals NC delta T. If, on the other hand, you're given a heat capacity that's in units of joules per gram per Kelvin, then you would need to multiply by the mass instead of by the moles, right? Because if you see grams in the units, you need to multiply by grams to get the units of grams to cancel out. This would give you the equation Q equals MC delta T, where M is the mass in units of grams, right? This is all about using the correct form of the equation so that you can get the units to cancel out. Now, we'll see both forms of the units of C in examples that we work over the course of this chapter and chapter 10 as well. So we'll get practice with using both of these equations and talk about in more detail, right? How you know when to use which form of the equation. But really, the units are the guide. One other thing that I'll mention here is when we're talking about the units of heat capacity, the temperature component of it can often be written as Kelvin, but it could also be written as degrees Celsius, and it doesn't matter one way or the other whether you use Kelvin or degrees Celsius here. I know that sounds kind of crazy because when we were doing problems that involved gases back in chapter 5, I said to always use Kelvin. But when we're doing these heat calculations and we're looking at delta T, the value of delta T will be the same regardless of whether you use Celsius or Kelvin. And so this is why the units don't matter. Just as an example, if you were to think about, let's say, changing the temperature of something from 0 degrees Celsius to 100 degrees Celsius, delta T would be 100 in degrees Celsius. If you were instead to convert everything into Kelvin, right? 0 degrees Celsius is 273 Kelvin. 100 degrees Celsius is 373 Kelvin. The change in temperature going from 273 to 373, the delta T in Kelvin is also 100. And so when you're looking at a delta T, it doesn't matter if you're dealing with temperature units that are in Celsius or Kelvin. So just be aware of that. You don't have to worry about temperature units here when you're doing a delta T. Next up, we're going to see an example where we're going to actually do some heat calculations.